So to start with, you're going to hear me talk about two things as we go through this tutorial. One is going to be type and the second is class. So when I'm talking about the type of an object or type of a data structure, this is how this is stored in memory. And the second is class, when this is going to define kind of what information is being contained within the data structure, and then secondly, how this can be used, what we can do with it. So the first structure we'll talk about today is a vector. So this is the simplest one and a kind of foundational for a lot of the other structures, data structures we're going to talk about. So there's several different ways to create a vector in R, but the two we're going to use is this first one right here, which is using this colon notation, which really just returns a sequence or returns a vector of sequences of numbers from in this case 1 to 10, a starting number to a second number. And the second one we're going to use is this C function. This stands for combine. And all this does is it takes all the input parameters here and it combines it into a vector. So if we run these two commands, you'll see that these both return vectors, and this returns a sequence of 1 through 10, and this returns a vector of these 6 elements in here, where each element is a different element of the vector. So as we're talking about vectors, the one thing to note is a vector has to be homogeneous. So the type of the element type in each of the parts of the vector, they all have to be the same. So they don't have to be numerics. So in this case, we can look at strings. So if I assign this vector here, cv.string, this is a vector of strings. It can be booleans or whatever, but they just have to be the same. So for example, if I try to create a vector with strings and a numeric, it's actually just going to coerce the numeric into a string. So it's going to find out the easiest way to make all these elements the exact same type. All right. So another thing to note is we can't really make a vector of vectors. At least that would no longer be a vector. So if I created two vectors, say v1 and v2, these are all numerics, and then I try to create a new vector that's made up of these two, all it's going to do is just combine those two vectors into one long vector. Okay. Now, I talked before about type and class. So if you remember, type is how it's stored, and class is what's contained or how you can actually use it. So there's two functions. One is type of, and the second is class, and this will give us the type and the class in this particular structure. So the type of v1 is double. So this is actually stored as double. And the class is numeric, so it means this contains numeric values, but also we can do numeric operations on it. That's what we can do. So if I wanted to do v1 plus v2, I could do that because its class type is numeric. On the other hand, if I looked at the type and class of the vector of strings, they're going to have different, right? So the type of for the string vector is going to be character. So it's stored as characters, and the class is character as well. So we can't do numeric operations, we can only do character operations on it. So if I tried to do like addition on this, I couldn't because it's a non-numeric, it's instead character. So I can't do, for example, arithmetic operations on it. I can also, like I said, create a logical vectors. So this is just using true and false. And you can see here I did this, and if we look at the type and class of that, we have logical, so it stores a logical, and you can use it as a logical. So that's how you create a vector in R, and also how you look at the type and class and how it's kind of stored and what you can do with it. Let's look at how you actually access the values within these vectors. So I'm going to create a vector, and this is just going to be the numerics 1 through 12. And the easiest way to access it is going to be this single bracket notation. So the name of the vector and then open and close single brackets with the element of the vector that you want. So for example, this v open bracket 5 close bracket is going to give me the fifth element of the vector v. Or I can actually input into this bracket notation a vector itself. So if I did this, right, this vector of 1 through 5, it's going to give me the first through fifth element um, of the vector v. Or I could, it doesn't have to necessarily be in order. I could create a vector of 1, 5, and 10, put it inside the brackets, and it's going to give me the first, fifth, and 10th element of that vector. Another thing I could do is I could do the negation. So if I do, say, in the brackets a -1, it's going to return every element except for the first one, right? Same thing, I could do -2, it would return everything but the second element, etc. And then using this bracket notation, I can actually change or assign values within the vector. So if I did, say, v in the bracket 15 equals 15, that'll just make the 15th element of this vector equal to 15. Now, something to note is that this vector is actually not of size 15, it's size 12. So if I do this, that's fine, because all this is going to do is now adjust the size of the vector, right? So it's going to extend it to size 15 and assign the 15th element the number 15. And the elements it doesn't have, see right here, this is the original vector, these 12. It extends it to 15, 1 to 15, assigns the 15th element the numeric 15, but we don't know values for this, so it fills in A here, which is how R handles missing values. So let's just reset this to 1 through 12 to work with real quick. The other thing you can do is input in a logical vector inside this bracket notation. So here I created a vector of true and false, and if I put this vector in the bracket notation here, what it's going to do is it's going to return true, false, the values, all the values corresponding to true within this vector, right? So that means it's going to return the first element and not the second one. Now notice that this vector right here is not the same length as the vector we're working with. So what that's going to do is just keep repeating this vector t until it reaches the length. So it's going to be true, false, and then concatenate another true, false on top of it. And extend that out until that vector is the same size as v, and then it's going to return all the elements corresponding to the value true. So right here it's going to be the first, third, fifth, seventh, ninth, and 11th. Okay, so this actually is really useful as you're doing analysis. So if I created another vector, and this is just going to have random numbers all over the place, okay, because I can do Boolean operations on a vector. So if I did, say, for example, v double equal sign 3, this is going to say v equals 3. So return a Boolean vector, right? If I do a Boolean like this, it returns a Boolean vector corresponding to whether the element or the indice of that vector is true or false according to this Boolean logic. So if we see here, the first and second element of this vector are 1 and 2, so those are both false because it's not equal to 3, but the third one, for example, is 3. So it returns true, and then false, true, etc. So it returns true wherever this, there is the element equals 3, right? Wherever this Boolean logic equals. So what's good about this is I can take this, some Boolean logic like that, and I can put it in, just as before, inside this bracket notation, and it'll return all the values where this Boolean holds true. So if I did v less than 6, it returns a Boolean vector where it's true, where each element, where it returns a true where each element that is less than 6 is located, and a false otherwise, and then I put that into these brackets and run it, and it will return a vector of all the elements of v that are less than 6. So that's a nice trick you can use, and it's very useful. So going beyond now, we're going to talk about matrices just really quick. And a matrix is the exact same thing as a vector, except the only difference is it has 2 dimensions. All right, so it still has to be homogeneous. It's stored the same way, but it can be in 2 dimensions now. So to create it, you can just use this matrix command, and then and you can have data equals, and that's going to be the vector, because again, like I said, it's the same thing as a vector, except for it's extended to 2 dimensions, and then the number of rows and number of columns you want. So if I run this, and print out M, then you see it's a two-dimensional vector, and it's going column by column, so 1, 2, 3, 4, 5, 6 by columns and not by rows. And that's a matrix. And then the next one, which is just an extension of both the vector and the matrix, is actually called an array. An array is just a multi-dimensional vector. Okay, so a matrix is actually just a two-dimensional array, for example. And to create an array, you just use the array command, and you input in the vector, because again, it's a vector stored the same way, and the dimensions. So you use dim equals and then whatever dimension you want. So I'll create two different ones here. One is two-dimensional, one is three-dimensional. So you can see that we can extend it beyond just 2 dimensions. So we can create this one, which is 3. If I print out the first one, you see it looks the same as a matrix. And if I print out the second one, A2, which is 3 dimensions, you see it right here. So this is the first of that third dimension. This is the first element of that third dimension, and this is the second element of that third dimension. So it's more or less like a 3-dimensional matrix, if that's what makes you feel better, but it's an array, it's in 3 dimensions. So they're very useful. Again, this is the same thing as just a vector, so they all have to be the same type, though, when you're doing it. So if I say type of and class of A2, right? The type is double, right? Because that's how it's stored. It's stored the same way as a vector is stored, just as a double. But the difference is the class. The class is an array because we can do array operations on it instead of just numeric operations, which you would do with a vector. But now you can do different things with an array. So that's what you can use that for. So let's just take a look at this this two-dimensional array real quick, which is really just a matrix. So if we look at it, first off, we see that itself is just a two-dimensional matrix. And if we want to index, get an element from here, we could just, same thing, we use these square brackets, but now we just add in an additional coordinate separated by a comma to get that. So this will give me the first row, first column value, which is 1. And then I can also leave one of these blank. So if I do A1 and then 1 comma and then leave that blank, what that's going to do is return the first row and then every single column. So this returns the first row and every single column in there. So it's going to return all columns. Likewise, if I didn't have the first row in there, I just left that blank and had the first column, it will return all rows for a particular column. So if I look at like the class of A1, it's going to be a matrix, and if it was A2, it would be an array, because A1 is just the two-dimensional version, which is just a matrix, which is two-dimensional array. So the class is matrix. As before up here, the class was array. That's just because matrix is a special case. And if we remember right here, these two elements, I return that first row and that first value. But if I do the class of these two, something interesting happens. I get numerics. So why is this? So when I get this first element, I'm just getting a single value. So it's actually just dropping everything else and returning that single value. And in R, there's actually no scalars. It's just one vectors of length 1. So that's what it returns, a vector. And for this second one right here, where I didn't put the column, it's returning this first, here's the value right here, it returns that first row, all columns, but what it does is it just drops that second row, so this is just, so this can now be stored as a vector, so it's returning a vector, okay? So that's why these two classes are the same as vectors, because they're dropping everything else. Let's say, for example, you didn't want to drop everything else, you still wanted it to be an array or a matrix, you can do that. You just have to use this drop command. So that's inside the brackets. You separate it by a comma, and you drop comma, and you do drop equals false. So if I do drop equals false to these guys and look at the class, now they're both matrix as before. So I can choose drop equals false, and it won't drop these the columns and rows that it's not using. It'll keep them and keep the same class structure. Otherwise, it will drop them and just return a vector. So depending on what you want, that can be useful. And then the next structure we're going to talk about is a list. Now these are really useful because there's two kind of distinguishing things about this as opposed to what we've looked at before. The first is each element can actually have a particular name. So for example, the value for this is string, is just the string, and the name of it is thing1. So I can index these by name now. The second is this can be heterogeneous. So for example, in list L, if I create a list L, and to do that I choose a list function, and then the name of that particular element equals the value of that element, I get a list. Okay, so this list now is actually a list of a string and a double. So it can be heterogeneous, and these each have their own name, which is thing1 and thing2. So if I do type of and class, I get type of list and class list because this is not stored as a particular value. They can be heterogeneous, so they stores it as a list, and also it's a class list, so you can do class list operations on it. Something else to note is I can make lists of lists. This is pretty interesting. So say I create these three lists right here, L1, 2, and 3. And L1 is just values 1, 2, and 3 with corresponding names. L2 is 4, 5, and 6. And L3 is 7, 8, 9, and 10. So notice that the length of these first two lists is 3. The length of the third one is 4. But that's fine. If I create these, I've created these three lists, I can actually make a list of lists. So I'll create a list L4, and this corresponds to a list of lists. So the first element is going to be L1. So this is a list of 3 elements, which is L1, 2, and 3. And then for each one of those elements, that's a list itself. Okay, so if I do type of L4, right, which is a list of lists, in the class, I still get a list. So a list of a list is still a list. Okay, so how do we index this? You can pull data from lists a little bit differently. So if I create a list, just say 1 through 10, corresponding names, 1, 2, 3, 4, all the way to 10. I can use a single bracket notation and input in a vector, so this will give me the first and second values, right? Something to note is when you use a single bracket notation with a list, it actually returns a list, not a vector. So this is a two-dimensional list it returns. So this is the first element, this is the second element. I can do L1, which is just still going to return a list. It's just a list of length 1 or size 1. I can do the negation as well, so it's going to return every element except for the second one. You can see here. All of them but the second one, so it goes from 1 to 3. But I can also access these by the name of the particular element using this $sign. So one, so I could do L $sign and the name of what I want to look at. So I do L $1, I get the first element. I can also have the single bracket notation and put 1 inside there, and this returns a single element too. Now note when I use this single bracket notation, it actually returns a list as well. So it doesn't return a vector as this did. Instead, it returns a list. But if I tried to do, say, ON, it wouldn't run, right? Because there's no element called ON in here. There's one, but there's not an element that is exactly ON. But that's okay because there's a way to get around this and do partial matching. So to do that, you just have to use double brackets instead. So now, in this case, you would do double brackets, and then you would separate a comma by comma and have this exact equals false in there. And doing that, it allows me to do partial matches. So here, TW, exact equals false, so it'll return the second element, which is 2, which is a 2 right there. So that's an interesting thing that you can do partial matches instead of just normal matches, or exact matches, excuse me. So if you remember L4 equals this list of list, we can also work with this too. So if I return the first element of this, it's going to return a list. right? Because it's a list of lists, and the first element is a list. But if I do the double bracket notation, it's not going to return a list. It's actually going to return the first element itself, which happens to be a list. But if you notice the difference is this actually returns a one-dimensional list, and that first value is actually a list itself. Where here it's just returning the value itself, which is just a list. So that's the difference. So I can also do vector notation, right? And this returns the first and second element, which are two lists, and I can do a vector notation again, except for using double brackets. And the interesting thing about this is now this says give me the first element of the list, which is another list, and then the second element of that list, which is a 2. So it gives me the first element of the list, which is the first element of this list, which is itself a list, right here, and then the second element of that, which is a 2, and that's what we have right here. So that's what this notation does. And then the last data structure we'll talk about is a data frame, and a data frame is just a vector, a list of named vectors. Okay, so the thing is one constraint is all the vectors in here have to be the same length, and since these are vectors, each individual vector has to be the same type. So this is going to be a list made up of 3 different vectors, but these 3 vectors have to have the same length, and they also have, within the vector itself, since they're vectors, have to be the same type. And to create a data frame, you choose data.frame, and that creates it for you. And data frames are really useful. So for example, when you load data in, even from database CSV, anything like that, they're usually stored as data frames in R. And then finally, just really quick, each of these data structures have what's called attributes. So for example, an attribute of a vector is the length. So I could do the command the length of a vector, and that'll give me the length of that vector, which is 16. It's more complicated, so I can just call the straight attributes function. Right, so over an array, and that's going to give me all the attributes. It's going to give me, in this case, it's only one attribute, which is dimension, and it's going to give me the values. But if there were more, I would see all the different attributes, or I could just, if I knew it was dimension I wanted, I could do dimension of that array. Same thing with a list. If I want to get the attributes of a list, I get it, and the only attribute it has is this name. So I could actually just call that function the names of L of that list, and it'll give me the exact same thing. And that's it. So that's a introduction to data structures in R. I hope you found it useful. And if you did, please like this video. And if you'd like to receive further videos regarding R or data science and machine learning related topics, please subscribe to my station. Thank you.